One of the things I want to say, though, just beforehand, is this talk's probably going to be a little bit different to the other talks that you've seen at the conference today, or that you're planning to see tomorrow. I've veered away from a very code-heavy, mathematical-heavy. It's very introductory, so I will not take offense if anybody wants to go to a different talk right now. It's quite introductory. It's more introducing the ideas and the concepts behind social network analysis and why you might implement something or where it came from. So honestly, if anyone wants to go, I'm not offended. That's totally fine. Otherwise, you've been prepared. So just to give a bit of an overview, I'm going to start about its origins and where it came from, and how it's evolved and its applications today. And as a part of that, I'm also going to talk about some basic network concepts as well. In part 2 of my talk, I'm going to talk about the data collection and preprocessing, as well as how I build the networks and then how I visualize the networks. And then finally, in step 3, I will show some of the results from visualizing and building the networks from the Star Wars scripts. So a long time ago, in the 18th century, many of you have probably heard of this problem before, and it's the Königsberg had 7 bridges in the city, and the citizens of the city had a sort of a game or a challenge. They suspected that it might be possible, or they wondered whether it was possible, to reach each of the land masses of the city by only crossing each of the bridges once. So in the diagram there, the bridges are the green stripes and the land mass is grey. And in fact, some people had claimed that they had actually done it. There is my feeble attempt. I was unable to do it. There are still at least 2 bridges there that I wouldn't be able to cover without repeating my tracks. So it took one of history's greatest mathematicians, Euler, in 1736, or not in 1736, to prove that it was in fact impossible. And the way that he did this was using graph theory, and as a result produced one of the first papers in the field of graph, well, the first ever paper in the field of graph theory. And the way that he proved this was he looked at the data, or he looked at the city, and he applied abstraction to it in ways people hadn't before. And he said, okay, let's take this and draw it on a page. Let's take the bridges and draw them as lines, and we'll simplify it, we'll model it, and we'll treat the land as dots or nodes. And as you can see as we move over, we get something where we have these blue circles, which nowadays we would call nodes or vertices, and we have these lines connecting them, which we call edges. And these edges serve as a record of the pair of nodes or land masses, that there's a connection between them. And it results in what we now call a graph. And what he proved using this method, or by graphing it, was that it's actually impossible to complete, because the only way that this problem can be solved is if all of your nodes had an equal number of edges leaving, or an equal number of edges in or out, apart from the first and the last nodes of the puzzle. So in the case of Königsberg, every single edge is an odd number, so it's absolutely impossible to ever complete this problem. And that was one of the first things that graph theory was applied to, and one of the first times information was extracted that way and solved. So graph theory itself it's relatively simple. We think of a graph as a set of nodes and edges. The nodes are the circles in this diagram, and the edges are the lines connecting those nodes, and they indicate an interaction, a relationship of some sort. And we can have different types of graphs. We can have an undirected graph, which is the one I have in the slide shown. And basically, this is undirected. You can't see arrows pointing on either end. And we can also have graphs that have weighted edges. So as you can see as well, these edges aren't just a consistent size. They're not uniform. Some are thicker than others. So in this case, you might think A and C have a stronger connection. If it's 2 people talking, this stronger edge between A and C means that they're talking a lot to each other and maybe excluding B a little bit in this case, where they both have a weaker connection. But we can also have directed graphs, and this is where the edges do point or indicate the direction of the communication. So one area that you might see this in is when people, say, leave a message on your Facebook wall. They have left an output of information. They've gone in your direction. So if I was to post on your Facebook wall, the arrow would go from me to you. And I would have an out degree of 1, you would have an in degree of 1. And so I say the word degree. And what is degree? So in this case, degree would be, if we look at node B has just a plain degree of 2. If we want to define it a little further, we could say it has an in degree of 2 because there's 2 arrows pointing in, but it also has an out degree of 2 because it has 2 arrows pointing out. Whereas if we look at C, this has an out degree of 2, and an in degree of 2 as well. And then, as well as we can have weighted naturally, we can also have unweighted graphs where every interaction is treated equal. And again, this type of interaction you might see when you friend someone on Facebook, because it has to be mutual. You can't have a stronger acceptance of friendship. You could start to weight it if you start to look at the number of posts you're sharing and things like that. So when did graph theory then move from being something that we can use to solve a simple, or not a simple puzzle, but a puzzle of that nature, into becoming something that we now use to model people with? And that's where Moreno's work came in the 1930s. He started to look at people and he started to model them as nodes and their interactions with each other as edges. In particular, he focused on a primary school and different classes in a primary school and how the kids interacted at the time. And one of the things he did was he put a lot of focus as well into the visualization of graphs. So the way that he started to model was he would, as I said, node a person, interaction, and edge, but he would also then give the nodes a different shape. He might say give a square to a woman, a triangle indicating a man. He would use different colors, and he would also change the locations of the nodes to try and encode more information into that graph. So we're starting to have this very visual representation of a lot of information that you don't have to technically interview people to get. You just have to watch their interactions or track their interactions. And I guess that's why one of the main reasons today it's synonymous with online social networks and social network analysis. The two seem to go hand in hand, and it's just because with all of this fortuitous data on how people are behaving and interacting online, social network analysis itself and the increased computational power that we have has been able to start looking at this data, this more large-scale social network analysis that you might see with Twitter, Facebook, LinkedIn, and GitHub. So when I say computational power, it means we can have computers now. We don't have to hand draw these graphs anymore. We have algorithms that will place the nodes for us. One of the desired things that we want when we're visualizing graphs is an algorithm that will try and reduce the number of overlapping edges to try and make it as clear as possible. But before we can build a network, we have to have data. Now, today I am using the Star Wars scripts for two reasons. I really like Star Wars, and then the other reason is it's a little bit more of an interesting problem than just taking a Twitter data set. Nothing wrong with Twitter, and there's nothing wrong at all with it. I use it probably too much, but it's quite a simple network to model because it's online, and the edges and the nodes themselves are quite explicit. So in this case, I want to just show you how we can also incorporate text analysis and how actually important it is when you start to look at areas outside the realm. So if you want to look at scripts, if you want to look at books or anything a little bit not as structured, not such structured data, there's a little bit more thought required. So in this case, the data that I used is from IMSDB, and I took the 7 scripts that were available there for Star Wars. How did I do this? I used Scrapey. I really like Scrapey. I think it's quite easy to use. I think the documentation is really clear, very simple. Maybe it's a little bit over the top for just getting 6 or 7 scripts, but I really like it. And I guess if there's anyone out there who is interested in how to scrape web pages, one of the things I would advise with Scrapey is it's very simple, the documentation is very clear. The only things that you kind of have to tweak with it are the tags on HTML pages themselves. So in this case, when I was trying to get the scripts, I would inspect the element tag or the HTML page. I would see that, and I mean, Chrome lets you do this very easily. And it's quite nice because I can just hover over wherever the script is or hover over the tags, the HTML tags you see there on your left. And it's under the TD class, it's called like screen text. So then when I have that text, I don't know if you can actually see when I actually have that text, then I put that into response CSS, and it's literally, for each of these scripts, bring me back. So I had the URLs, and then I was doing a little bit of manipulation on them just to get the name of them and store the name of the scripts as well. And then the script itself, so the little asterisk there just means get all of the text between the tags, the td.scr text tags. One of the reasons for this is because if you don't have the asterisk there, it won't take bold text, it won't take like sort of slightly spanned text or different text in that way, so it just takes everything for you in an extract. So that was nice, that's it. It stores in a JSON format and you have your data relatively easily. Hardest part is the text preprocessing, in my opinion, and probably might take up the majority of this talk a little bit. Because one of the things, as I was saying, with Twitter being like explicit connections and Facebook being explicit connections, with text data, you just don't have that. Now, one of the things I was looking at, I was going between 2 ideas when I was processing this text. I was like, okay, will I just go online and see if someone has the characters all listed out for me, take that dictionary, find the characters, there's my character list. And I did see one, and there's lots of dispute. So fans themselves argue over who's a character and who's not a character. And this is it. Like, there's so many things that have to be considered. You're not going to please everyone, and you have to keep reminding yourself and remembering you're building a model. Your thoughts and your ideas are going into that model. So just be aware that it's never a definitive. The models can be different. You can model this network differently. And what you call a character and don't call a character may be different to somebody else. So in the end, I decided, okay, I'm going to use the scripts and I will look at the characters that I see in there. So one of the things about the scripts themselves is I have to identify when is a character occurring. And I thought it would be it is actually quite simple for scripts. In comparison to a book or other types of text formats, your character is quite explicit in the sense that there's a character name, this is what they said, here's the scene they're in. So I can't really complain in that area as such, but you also have to make a choice in how far or how deep are you going to go into collecting every mention of a character in a script. You also have the idea of, well, when do I define they're in the same scene or not? Once again, thankfully, all of the scripts had the same sort of formatting in that sense, that they all followed this int and ext, like in enter scene and exit scene kind of tags. So I could just look between them and define that as my scene. But really, overall, the scripts were all quite different. And so these are just 3 examples of so in number 1, you can see that the character, its center, they're all capitalized and they're above a little paragraph, which is also centered to say that they were talking. And then the paragraph underneath is like a bit more background detail about that scene. In number 2, the characters are defined, they're on the same line as the text information, and you have your semicolon, or not your semicolon, colon. And then you also have in number 3, your characters are again on their own line and all capitalized. So again, one of the things that was nice is when speaking character, they were capitalized. So I had that to go by as well. Other problems with characters, though, would be they can have multiple names, okay? So you want to try and define a definitive name and make sure that whenever you come across those, that you're getting the right character. So in this case, there is, so in number 1, there is a blog post of somebody who has done social network analysis with Star Wars, but using F#. And she had already come up with an alias list, so I was a little bit cheeky and borrowed it for this. But I added a bit of my own. I found spelling mistakes and stuff like that, so in number 2, and there was more than just Anakin, but spelling of Anakin seemed to be an issue. So I had to come up with some, I had to just enter that into an alias and have that as my definitive name. So these small little things like R2 and Threepio, we would usually, well, I would usually see them as C3PO, as you can see in the name side. But otherwise, basically, there was always a little tweak for each of the scripts. So it wasn't like a nice, clean, automated, fully automated process. You do have to stay in the loop somewhat and say, okay, depending on the level of abstraction that you want or the level of extraction that you want. Leading white space counts, though, amazing. I really like them. And uppercase was handy as well, but yeah. And so, what am I going to count as an interaction between these characters? In this case, I decided that I'm not going to count when other characters mention somebody else if they're not in the scene. So I've given 2 examples here, not related to Star Wars, unfortunately, I'm sorry. These are from Bleak House by, oh wow, Dickens. Yeah, thank you. And in this case, we see Lady Deadlock's cause has been again before the Lord Chancellor. Has it, Mr. Blah, blah, blah? I'm not very good at pronouncing stuff. Tulkinghorn. Anyway, so in this case, the Lord Chancellor and Mr. Tulkinghorn are in the scene, but Lady Deadlock is not. And this is coplanar, so I'm not connecting them all entirely. And this is what we call a coplanar interaction, and it's very suitable for kind of dialogue interactions. If you want to take interactions that are not just dialogue, and in the case of novels, you probably do, because a lot of the time you'll have chapters where characters say nothing, but they do a lot of things. And in those cases, you might want to go for something between collinear and coplanar. But because I'm dealing with scripts and there's very little, okay, there is some descriptions, but most of it is action and the characters are talking to each other. So I went with coplanar or collinear. Since I'm already digging into the text itself, something I'm also interested in, and I like kind of expanding what we can learn from networks and how we can complement networks further, is sentiment analysis. So I use text blob in this case. Again, very simple. Literally download text blob, import it, put text blob before the text that you want to analyze, and you can just say .sentiment. You can also, there's further arguments there, but this was literally what I did, just to see when a character is talking to somebody else, was it negative, was it positive? I want to see if the interaction, I wanted to get a further piece of information from that, just to see, okay, are we going to see more negative interactions with Darth Vader or more positive around Luke? Who knows? So I thought it would be interesting. And now we're on to Network X. And this is what I mean by, like, this is literally the only slide where I'm going to show you code from Network X, because it feels for me like the simplest part of creating a network is literally going, I've already defined my edges, I've already defined my nodes. All I need to do now is like link them together, and Network X does that amazingly. Those commands right there will put a network together for you. Now, the other thing about Network X that I'm not going to go into today, though, is that it really does have a lot of options for analyzing networks, such as a lot of different centrality measures. You can do some community detection with it. You can do link prediction, even modularity. There's so many things, and it's well documented. But because I wanted to keep it introductory, but for anyone else out there curious who wants to see what else it can do a lot. But once you have your networks, and you do that via Network X, you have like a few options now for network visualization. So Donald E. Knuth has a nice quote: "Graph drawing is the best possible field I can think of. It merges the aesthetics of mathematical beauty and wonderful algorithms. It therefore provides a harmonic balance between the left and the right side of the brains. And I like that because I think it really hits the nail on the head, because you are merging all of these different fields. And with graph theory, it really is applicable to lots of different fields. It's applicable to humans, it's applicable to nature, it's applicable to biology. And I went and I used Gephi. So there's the option to continue using Python for your network visualizations. There are libraries out there. Reason I'm using Gephi, and I would recommend Gephi to a beginner, is because you're going to build your network, and one of the things I think you want to grasp first is, well, what are the different ways you can visualize a network, and what does it mean? And it lets you quickly apply different network centralities to your data. So you can get quite a fast output without having to write too much code. And then when you want to dig a bit deeper, then you can start to contribute maybe to Network X, when you've got more of a bearing of what all the different centralities mean and the different concepts behind it. So I think Gephi is a nice application, and Network X handily, as you can see here, outputs to it. One of the things is, it is, I'm not going to lie, it can be a little bit buggy. And there just seem to be some sort of installation issues if you're using a Mac with JRE, but otherwise there are blog posts out there and they'll walk you through it. And these are the types of networks that you'll get. I've sort of zoomed in there, but it'll even change the font size for you. Something, if you're doing in matplotlib, takes a little bit longer. And when you're not entirely sure how you want to visualize it, it's really nice to get a fast, quick idea. So this is the first network I'm going to show you. I find it kind of amusing. Basically, what you're seeing is Threepio in the middle. He has the highest weighted degree. So he has a lot of interactions coming into him, and he has a lot of interactions going out. And if you see the color of these interactions, they're quite red. And in this scenario, it's where Luke Skywalker says to Jabba that basically you can have Threepio, and Threepio starts to have a bit of a breakdown and is like, no, 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 why would he do this to me? And it's just interesting to see all of the negative interactions around that little scene. So that's one scene. But the other thing you might notice is his pal is missing, R2D2. So this is one of the earlier networks that I visualized without my aliases, just to get a feel. And I'm like, oh, well, you can't have Threepio without R2D2. And that's when you start to go back, and it's an iterative process sometimes. You see things and you pick them up and you're like, okay, I need to go back. I need to fix that. And also the character names in this case haven't been normalized yet either. So we have Threepio spelled out. But what we can do when we have our graphs, so we can start to characterize the graphs themselves without necessarily going onto an individual level. So there's different granularities that you can look at with network analysis. You can start to compare whole graphs to each other to get an idea. So in this case, one of the things you might want to do is, can we define properties or look at properties of this graph that would make it unique or make it look fictional in comparison to if I took a graph from Twitter, which is of real life. But another thing as well is the density of the graph, which I'm showing here. And graph density is something quite nice. Again, Network X and also Gephi both implement quite quickly and easily. And it's basically, if you have the same amount of edges in each graph, or the same amount of nodes or circles in each graph, if one of them has a large amount of edges, naturally it's quite dense. There's a lot of interactions. So we could be having a large discussion just between 4 of us or something. And then in the sparse graph here, we have a lot more nodes than we have edges. So there's a lot of maybe just one ping or one interaction in those types of graphs. So I decided that might be one of the ways I'll have a look and see if I can quantify the differences between our graphs. So this slide gives a bit of the numbers behind it, and this slide tries to visualize them a little bit. It probably wasn't the smartest idea to try and fit 7 onto the same page, but there you go. Hopefully you can still see the names quite large, and maybe even, in fact, it might be a little bit more interesting because you can sort of see, right, we have number 1, number 2, and number 3. So these are not the first 3, but the ladder 3 before number 7, and it's where Anakin's story is told, and we can see that Anakin is quite prominent in these networks. And these, I should say that the nodes are sized by the weighted degree again. So I'm not using the in or the out degree at this point, I'm just looking at plain weighted degree. And in this case, that just, Anakin has a lot of in and out interactions again. Obi-Wan Kenobi becomes a bit more prominent in number 2, and then we see the two of them kind of taking center stage along with the Emperor in number 3. And if we actually go back and we look at this, the Phantom Menace, which is the first one, has the highest density, but it's quite a small network as well, but it has a lot of edges. Now, as much as I like Star Wars, I'm not a complete expert. My theory behind this would be that it is quite a centralized story on the kid, on him as a kid. And so his social network at that point in time isn't going to be it's not going to be large. He's going to be mostly around the same characters. And you wouldn't really expect a kid to have a massive social network at that point. And I think it's interesting to see that reflected in the film itself and how it was written. One of the other things that we can look at are network centralities themselves. So this is zooming in, going into a more granular look and looking at the people themselves and starting to characterize the characters or the nodes. And as I've explained a few times now, degree is probably the simplest one you'll encounter, where I'm saying in degree or out degree, literally the number of edges. And right now, as a little bit of an aside, I'm looking at link prediction in networks, and one of the most predictive features are these really simple local features, such as degree, in degree, and out degree, which is really interesting and surprising. And from what I hear is also, it makes it easy. Well, for me, it makes it easier to compute rather than having to look over the whole network. You can start to see whether people will connect or not. So I wouldn't take for granted just because they're simple does not mean that they're not powerful. When we look at weighted degree centrality for this network, so I should describe what this network is. This is basically an aggregation of all of them. I got curious. I wanted to see what happens when I aggregate all the networks and see if we can see anything else sort of shining through the data in that sense. They do, I mean, this is the other side of it. I mean, the way that I built these networks, I mean, it shouldn't be surprising in a way that we see them clustering into their respective episodes and series of episodes, I guess. And then down at the bottom here, we can see the latest film, The Force Awakens. And I think it's interesting that we see it more on this side than we do with its sooner or more previous films, I guess, even though they're backwards in the story. That sentence made no sense, and I apologize. Hopefully you get what I mean. But with the weighted degree, we can see that out of all of the characters in the network, Obi-Wan Kenobi and Anakin really seem to play an important role throughout the entire film series. Of course, we still haven't seen the rest of Rey and Finn's roles, so who knows, they might expand, but I guess they have a lot of catching up to do in that sense. So yes, they are important, but we also have more information on them. So you've got to always be aware of when you're saying these things, it's not, yep, definitely the most important with the information that we have. For the Betweenness, now I really like Betweenness. It's one of my favorite centralities because I really like understanding how information is flowing between two different groups and user roles and things like that. And Betweenness is a centrality that's very useful. So they're the brokers or the bridges. So if you have a clustered, isolated group over here and you're wondering how information is going to transfer to them, you're going to have these people who have sort of weak links between them, but they're the ones that are transferring that information and expanding that information and moving it around. And one of the things that, when we look at it in the context of Star Wars, Obi-Wan Kenobi, or Obi-Wan, whatever you prefer, seems to be that person. He is that bridge between all of our kind of different networks of characters in this. And he's the one that ties them all together and has the information broker in Star Wars. but also so is Darth Vader, which is surprising. He interacts, but he doesn't seem to have that much contact. But that is also something to take note of. Obi, Luke, and Darth Vader are these bridges between the different worlds in that sense. Just to finish, I focused in a little bit more on The Force Awakens and showed the two comparisons. And I also visualized the graphs a little bit differently, in this case, to show another variation. So in the previous graphs, I used something called Force Atlas, and these ones I'm using Rutherford Ringgold. And I'm just showing the comparison between betweenness centrality and weighted degree. And what I like about this is, for me, betweenness makes sense. Poe does kind of go in between all of those different sectors or different people in the film. But what I get from weighted degree is that it seems to be like more of a sign of friendship in this film. And we know that there's strong bonds between Rey, Finn, and Han. But where is Luke? So when I was complete and I finished everything, and I looked at these networks and I was like, okay, Luke's not appearing in The Force Awakens. And obviously, and I'm really sorry, people, there's probably spoilers coming along, but he doesn't talk. He doesn't talk in the film, so my networks completely miss out on him. And this is where it's important this is where mentions become important. This is where your auxiliary information also becomes important. And this is what I mean by there's so many different ways to model a network. What information is it that you want to learn about that network or those people or those ideas that you want to learn more about? There's some resources and references, and that's my talk, and I will be happy to answer any questions that you have. Thank you for listening.